Welcome back. This another session of principles of communication systems. We are discussing about Model 5. Sampling theorem was dealt in detail bit in Model 4 and continuing the same thing in Model 5. So quantization also we have discussed. So let us see about the pulse code modulation. So it is a process where it is going to see that our message signal, that is M of t, or a modulating signal M of t, is represented by a train of coded pulses, a set of coded pulses. So in that way we can say that we are able to convert our message signal in the form of discrete, either in both time and amplitude. Means what this PCM is doing, it is simply trying to convert, it will simply transforms our message signal M of t in a discrete form with both time and amplitude. That's all, by using a set of coded pulses. So let us see how this could be achieved by using some of the important blocks of the PCM. Like here you can see transmitter is there and receiver is there. So two are the important blocks of the PCM system along with the transmission path. So you can see it start with one by one. Pulse code modulation. So here you can see if you take a transmitter block of the PCM system, it will start with the source of continuous time message signal. Means this is your information signal or information carrying signal or baseband signal M of t or modulating signal. I'm using the set of words modulating signal here just to give the implication that uh, we all the way used that word for the message signal, that is a modulating signal. Of course, we are using that modulation process later here. So followed with that one, we have the low pass filter or pre-aliasing filters. These are known as pre-aliasing filters because this is the first low pass filter which is appearing before the input message signal. So message signal is first going to pass through this LPF. That's why it is known as a pre-aliasing filter. So pre means in advance we are doing taking care of aliasing effect here. So whatever the information you are transmitting, no, without aliasing or overlapping, they should be transmitted through the common channel. So common channel is there here. You can see the transmission path. So that will be taken care by low pass filter. Then another job of this LPF is to avoid any high frequency noise components. So two jobs this LPF is doing. One, it is avoiding any high frequency noise contents. Second thing, it is taking care of aliasing effect on the part of signals to be transmitted over common path or transmission path. Then that signal is applied as input to the sampler or sampling process. Here we can see I have taken here instead of so far in my previous videos, you have seen some colorful quotations, but instead I am using this new typical method here just to give the glimpse that because I came to know that much of you are uh, referring, uh, not referring to the books there, books or notes. So just to give the glimpse that if you read the notes or textbook, how it could be, in what way it could be done. So this I have taken the glimpse of sampling context from the textbook here, and this one is from the notes. Now we have to explain the sampling block here, sampler. We already discussed about the sampling process in detail in the previous module. So let us try to briefly apply that same thing here as a part of this PCM. So incoming message signal which got aliased and high frequency components removed. No? So then we are going to, what sampling we are doing? We are going to cut that continuous time domain message signal. Even when we passed that message signal through LPF, doesn't mean that it has lost its continuous time domain property. It is still continuous time domain signal. We have to convert that one into discrete or digital domain. So these three blocks, what you are observing, no, sampler, quantizer, and encoder. These are the, you can think of them as three integral parts of any A to D converter. These three blocks you can see here. What are those three blocks? So this is the key point here. You have to remember, sampler, quantizer, encoder are going to be three important integral parts of any A to D converter. They are simply doing A to D conversion, ADC here. So what is happening with the sampling here? It will simply has to do the duty of cutting your continuous time domain signal. Here it has been written here. The incoming message signal is sampled with a train of narrow rectangular pulses so that uh, will achieve instantaneous sampling process. We are doing instantaneous sampling process. Means our incoming message signal is sampled with a train of rectangular pulses as a part of instantaneous sampling process. This is how we have to try to write it. But in order to ensure that, we'll also have to ensure, so whatever the samples you are getting by cutting that continuous time domain signal, so those samples property should be such that that sampling rate, at what rate you do the cutting or sampling, so that that will be decided, it should be according to the sampling theory. So here it will be quoted here, you can see the sampling rate so must be greater than or equal to twice that of the high frequency component W of the message signal. So this condition, according to this condition, the sampling should be done. And moreover, already what I already mentioned, a pre-LAS or low-pass filter is used at the front end of the sampler to avoid any or to exclude high frequency components greater than W. So that will be treated as noise here. Okay. So these are the two important things here. So thus the application of sampling allows the reduction of continuously varying message signal to a limited number of discrete values per second. What does it means? So guys, this whole para, after reading this one, you may not understand it once or twice. You read it once or twice, try to understand. It may require some back things to read there. So how you write down the main points as far as the sampler block you are going to explain here so far. So about this block, source of continuous time message signal I already explained, and about low pass pre-alias filter also I already explained. So he have to mention here in the first or beginning why it is called or mentioned as pre-alias low pass filter, because it will be used at the front end of the sampler, because the message signal is first what low pass filter it is reaching message signal, that is known as a pre-alias filter, or another reason it is there in the front end of the sampler. So why it will be kept in the front end of the sampler? Because we want to exclude, not include, we want to exclude high frequency components which are greater than the high frequency component residing in the message signal. That should not be mixed with M of t. And it will be treated as a noisier or unwanted signal. That should be excluded. And second thing, it will take care of aliasing, overlapping between the samples. So after taking these two things, the input will be given to the sampler. So that is going to do the sampling of your continuous message signal into a number of samples, so that satisfying the condition, the sampling rate should be greater than or equal to 2W. So in this way, the sampler is simply converting your continuous message signal, time domain message signal, into a number of discrete values, a set of discrete values. So output of sampler nothing but will get a set of discrete values. That's all. So this is how you have to explain about the sampler block. So you can see here. So initially you applied your source of continuous time domain message signal, raw message signal M of t. It will be passed through low pass filter. So at the output of LPF you will be getting only lower frequency components without aliasing of this M of t. No samples, it is continuous time domain signal only still. Then that will be applied as input to sampler. Then at the output of sampler you can see now will not be having any continuous time domain signal. Now we'll be having a set of discrete values. Your continuous time domain signal is now converted to a set of discrete values which are now to be taken per second to do the next process that is called quantization. So the sampled version of message signal is then quantized, providing a new representation of message signal that is a discrete in both time and that's how I told. The continuous time signal is now converted to a set of discrete values in both time and amplitude at the output of sample. So that will be given now as input to the quantizer. So guys, the quantization could be done in two different ways. One is uniform or linear quantization. So in contrast to that, already we have discussed in the last session, mid-thread or mid-riser quantizer. And for non-uniform quantization, we normally used mu and yellow. So the use of a non-uniform quantizer is equivalent. So you can see here, for example, so this one for mid-thread or mid-riser. That is coming under uniform quantization. So whatever we have discussed in the last session, that we can try to use those sentences briefly here to accommodate the explanation for the uniform quantization. So I will go with the non-uniform quantization. So use of non-uniform quantizer is similar to passing the baseband signal, that is a message signal, through a compressor. We are trying to compress here by applying a compressed signal to a uniform quantizer by using this mathematical function. A specific form of compression law, you can see here that compressor is going to follow this particular principle or a law that is used in practice is called a mu law. You can see the amplitude, this is the message signal, this is the reconstructed signal V, log of 1 plus mu of m divided by log of 1 plus m. So the graph here you can see it is going to show you the behavior of the mu law in terms of mu of m. So it is a plot of normalized input, that is a m, and here V it will be indicating output, normalized output. M versus V we are plotting with the various values of the mu values. So here guys you can see mu equal to 0, it will indicate uniform quantization. If you take mu equal to 0, it will be simply uniform or linear quantization. Other than that, on either side, if you go on increasing the mu value in a positive way, you will get the curves bending on the towards the top left corner. And if you go on getting the mu values less than 0, that is negative, you will go on getting the curve bulging towards the bottom right corner. So here it has been shown here. So the mu equal to 0, you can see the sample of the text glimpse I have taken here. It is indicating a uniform quantization line. For a given value of mu, the reciprocal slope of compression curve. These are the compression curve. You can see one compression curve we have got for mu equal to 5, and another compression curve we are getting which is appears to be more bulging with mu equal to 100, which defines, so this bulging or slope, so more bulging means more slope means more quantum steps. So that is decided by or governed by this equation, or simply doing derivation of this equation 1, that is V with respect to mu. Or after that you will take the ratio of dm by dv. Or else you can do for the m equation, derive it with respect to V. So this is a new equation we are getting. If you want, you can call it as equation number 2. So therefore, the mu law is neither strictly linear nor strictly logarithmic because of this variation of the mu that it is going to depend on this equation. You can see that this function is going to depend totally on the mu value. But it is approximately linear at low input levels for the values very much less than 1. You can see mu equal to 0 or very much nearly equal to 0. That's what he is telling, mu of m very much less than 1. And approximately logarithmic higher input levels. So the upper part you can see very much larger than 1. So this how guys you need to explain about the quantization, both linear. Linear part you have to accommodate from the previous session explanation, whatever we have did. And non-linear quantization explanation, that is behaving like a compressor. So main key point here is that it is neither linear, non-logarithmic, non-linear. So totally dynamic here because it is going to depend on, heavily depending on the mu function here, mu parameter. So that's why you can see here it has got its name as a mu law. Is it clear? So another expression for the mu law is used in practice is also called as a law. A means amplitude here you can see. So normalized input m, it is going how it is going to vary with the different values of the amplitude. So if you keep the amplitude value lying between 0 to 1 by a for m, so output is going to follow this function. And if you are going to keep the amplitude value from where we left out 1 by a to 1, so totally we are going to vary from 0 to 1. But the behavior is going to be different here. So that's why we got two different expressions here. So here the first term you can see a of m divided by 1 plus log of a is partially logarithmic. But the second term, when you are going to vary a as per the a law from 1 by a to m, it is going to be appears to be totally logarithmic. So practical values of a tend to be in close proximity to the 100 here. 100 we have shown here. So the case of uniform quantization corresponds to a equal to 1 as far as a law is concerned. Whereas mu law is concerned, mu equal to 0 corresponds to uniform quantization. You can see these are the two important key statements should be there in your answers. So in case of mu law, mu equal to 0 corresponds to uniform quantization, whereas in a law, the a equal to 1 corresponds to uniform quantization. So where in mu law, the whole curve behavior depends on their bulging or slope variation, whereas in case of a law, you can see the variation of a, the amplitude is going to recover or govern the behavior of these curves in the air. The reciprocal slope of this compression curve is given by again deriving m with respect to v as we did in the previous case in this equation. You can see 7.48. Okay. Again, we are getting two separate terms here, partially logarithmic and fully. Both the terms now we are getting fully logarithmic functions. So after doing pre-aliasing or avoiding high frequency components, then sampling it, converting into a set of discrete values, and after doing the quantization setup there, we'll have to do. So quantization means what we have did there? We have simply decided what nearest values to be assigned to each of the sample. Still we are not yet assigned. So that could be done with the help of encoder. So that's what he is telling here. So in combining the sampling and quantizing, the specification of continuous message or baseband signal becomes limited to discrete set of values, but not in the form suited for transmission over radio path. So this is a very important statement, guys. So how you can elaborate or explain or understand this one? Okay, we converted continuous time domain signal into discrete values. Discrete set of values will be converted with the help of quantizer into some nearest analog values to be assigned. Then later, these samples with the analog nearest values, what he is telling are not suitable to be transmitted over the radio path or communication path. So what we have to do? We have to do the coding process here. Why? Because the purpose of making the transmitted signal more robust to noise or interference and other channel degradations, we need encoding process. So what this encoding process will do? It will translate discrete set of sample values to more appropriate form of signal. This is very important, guys. Try to understand here the main concept of coding. Even we estimated a nearest value for each sample, that is analog value. Okay. So that analog value should be converted to some binary or basically some coding format. So that could be assigned. But why that coding is required? Coding is required. The necessary or sufficient reason is coding here to make our transmitting signal more immune to noise, interference, and any other channel degradation. Very three important terms here. That's why we are doing encoding process. So with the help of this reason, we are doing encoding process, and thereby we are in a position to translate a set of uh, discrete set of values into quantization levels or discrete values with the help of this coding process. So one of the process of doing this coding is either we can select the terms at a time, or we can select the group of bits at a time based on bit interleaving or word interleaving. So two types are coming. Let us see one by one. So how the things are going to work out in the binary codings here. So the maximum advantage of doing this encoding process is advantage of that one. Effects of noise in transmission medium is obtained by using a binary code. Try to understand this. Effects of noise in a transmission medium is we can get it by using binary code because binary symbol withstands relatively high level of noise and is easy to regenerate. So this is very important. Even though we came to know that our transmitting signal after the output of quantizer, a set of discrete levels are not suitable to be transmitted over one common transmission path. Of course, we can do the coding, but why only coding? Why that too only binary coding? Because you can see in binary coding we have only two representations, either 1 or 0. So these two representations are providing very high immune to the noise. Resistance to noise is sensitivity to noise is reduced, and these bits are easy to regenerate once again if you lost it. Suppose if you take R bits for one sample to represent, then we can represent that sample with 2 to the power R levels. Suppose if you are going to represent one sample with the 2 bits, then we can have 4 level of representation for that one sample. You can see, for example, this table. If you take the number of representation of levels, 0 if you take 2 to the power of 0, only 1 level. If you take 1 2 to the power 1, only 2 different levels you can represent that sample. Similarly, if you take 3 2 to the power of 3, you can have in 8 different ways, 2 to the power of 3, 8 different ways we can represent that sample. So that is a 3 you can see here how is representing here. So 3 value is will be coding here. Okay. 2 to the power of 0 plus 2 to the power of 1. He is trying to calculate the number of levels here by using this way, this formula. But we know already how 2 to the power of r will give us different levels of representation for the one sample. So this is the binary coding concept. Let us see what are the different level or line codes which are available for us. So let us consider an example, one code or data we take. In encoder, what we are doing, we are converting the binary stream of data like this, for example, into electrical representation. So this is, guys, you can remember, this is the electrical representation of binary stream. stream of data. So this is the electrical signal that we actually wanted to transmit. Understanding this one? So again, two terms you need to explain here, NRZ and RZ. NRZ means non-returning zero. Means whatever the sample you are representing by the pulse, so that pulse is not returning back to zero. That is a non-returning zero concept. Returning zero concept means pulse is going to return back to zero while you are going to use that pulse to represent the sample. So let us see one by one different line codes which are available. In that, the first one, unipolar non to return zero signaling. So here, one is represented by a pulse of amplitude A as shown in this figure. Here you can see for 0 we are not sending anything, off pulse will be sent. For 1 bit, one square wave pulse of amplitude A will be sent. So this will be maintained at a, because next pulse is also going to be 1 year. Two successive ones came. After that we got 0, off pulse will be there. After that 1 will be there, one single pulse of one amplitude A will be sent. Again we will be getting two successive zeros, two off pulses will be sent, and after that one digit will be there, that will be represented by or coded by sending one pulse of amplitude A. So that's why you can say this is also known as on-off signaling. This method of coding, unipolar NRZ signaling, is also known as on-off signaling. So the main drawback of this technique is the waste of power because of transmitted DC level. Because we are transmitting plus A. Plus A means maybe 5 volt or 2 volt, whatever. That is fixed. So that will encounter into the loss of power while you are doing a transmitted DC level. So next one you can see with respect to this pattern only, polar, unipolar means on one side of the origin, top side only we got. Now same thing bipolar, on either side of the 0 now we are getting. Now symbol 1 is 0 is now represented with minus C, and 1 is represented with plus C, that's all. You can see symbol 1s and 0, sorry, symbols 1s and 0 are represented by transmitting pulses of plus A and minus A, correct. 1 is by plus A and 0 by minus A. So you can see here 0 by minus 1, 1, 2 successive ones you got, 2 plus A, 1 0 you got, 0 should come a little bit here, that is a negative minus A. 1 again it is represented by plus A. Again, two successive zeros are represented by two successive minuses, and one last one digit by 1 plus A. That is a polar NRZ signal. So that's why you can see this line code is relatively easy to generate and is more power efficient than its unipolar counterpart. So like that, this is also important. So whenever you get a question, explain about different line codes. Don't simply explain about their techniques. Also, we can try to compare successively with the previous one, how they are power efficient, how they are more advantages, or having the limitations compared to the other techniques like that. Next one we got unipolar. Unipolar means on one side of the top side of the origin, return zero signal. So here symbol 1 is represented by the rectangular pulse of amplitude A and half symbol width for the symbol 1. And 0 is represented by transmitting no pulse. You can see, for example, you can easily understand here this one. 0 you can see represented by no pulse, okay. 1 is represented by 1 square wave pulse of amplitude A and 1 half pulse. So these two combination will pair one non-zero plus A plus and one zero pulse. Will make out one digit representation. Another one digit representation is by another successive, another one digit is represented by another square rectangular pulse of amplitude A with half symbol, like that. So as it has been shown here. So the main important feature of this method is that so presence of delta functions at 0 plus or plus 1 by TB minus 1 by TB in the power spectrum of the transmitted signal. Means if you take the power spectrum of this one, there will get delta functions located at the origin, that is f equal to 0, and symmetrically at on either side of the origin, that is 1 by 2b and 1 minus 1 by tb on other side, which can be used for bit timing recovery at the receiver. This is very important feature of this unipolar RZ signaling. But it itself will become a limitation that it requires 3 dB more power than polar return 0 signal. So one advantage and one disadvantage like this. About bipolar RZ signaling. So far you can see whatever so far let me briefly summarize here whatever you did. Unipolar NRZ, polar NRZ, unipolar NRZ, polar NRZ, unipolar RZ, bipolar RZ. So like that, 4 2 with respect to NRZ and 2 with respect to RZ. Very. So specifically in bipolar RZ signaling, positive and negative pulses of equal amplitude are alternatively used for symbol 1. We can see here, with each pulse having half symbol width. No pulse is used for symbol 0. So hence, this useful property of BRS signaling, that is a power spectrum of transmitted signal, has now you can see no DC component will be there, no power loss, and relatively insignificant low frequency components for the case when 1 and 0 with equal probability are used. Hence, this coding is also known as alternate mark inversion signal. So the fifth one is a split mass phase coding or a Manchester coding. So in this method, symbol 1 is represented by positive pulse of amplitude A followed by negative pulse of amplitude minus A, with both pulse being half symbol wide. This is very important. ಇಲ್ಲಿತನ ಒಂದು ಫುಲ್ ಸಿಂಬಲ್ ಒಂದು ಹಾಫ್ ಸಿಂಬಲ್ ಇರ್ತಿತ್ತು, ಈಗ ಎರಡು ಹಾಫ್ ಸಿಂಬಲ್ ಇರ್ತವೆ. For symbol 0, polarities of these two pulses are reversed. This is very important. That's why it is known as a split. We are not sending nothing or 0 for 0 now. What we are sending for 1, now we are going to send for 0. Let me repeat. So this is called split phase coding because we are sending what we are sending for 1, its exact reverse now we are sending for 0 representation. That's why it is known as split phase coding. So Manchester code suppresses the DC component and it has relatively insignificant low frequency components with respect of signal statistics. So this property is important in some of the applications. Like that, guys, you try to briefly explain all these 5 coding techniques whenever we get PCM, or specifically sometimes you may get some problems on this one. Last question paper he has asked on coding by using any one of these unipolar NRZ or unipolar NRZ, bipolar NRZ, or unipolar RZ, bipolar RZ, or split phase coding like that. Specifically, you make a numerical or a question on this one. If you get a question on PCM, briefly you have to explain about that. So next class we are going to discuss about so continue with this one. Transmission path we have at this point now. Next class I am going to explore with a brief explanation once again for you to find. We'll see the transmission path in detail along with the receiver in detail. Thank you.